So hello and welcome to our third class in the exobiology course. This is our the third astrophysics class and the final final class in this astrophysical part of the exobiology class, which is divided into three parts this year. And I'm just doing the first part on the cosmology and astrophysics. And I want to start this third class with a little summary of what we've set up till now, and then continue with the search for water for two other parts: the search for water in the cosmos and the formation of planetary systems. So this first video will just cover the resume, the summary, and the discussion of the lifespan of stars. So in the first two classes, we said that the field of exobiology is a multidisciplinary field in which we're interested in the question of the existence of life beyond our planet. It's a multidisciplinary field, but in the astrophysical part of our class, we're going to concern ourselves with the abundance of shelters on which life might conceivably form. Now, we're a bit limited to life as we know it, and therefore our list will not be a definitive list. It's meant to more be a provisional list, a reasonable list. Sometimes in science we have to do this because the questions are just too interesting or too important to not address them, or to wait until we have definitive answers to things. So what do we do in this case? Well, we search for, when we're looking for a shelter for life as we know it, we look for a sun, in quotation marks, and a planet, an Earth-like planet around that sun. And we would expect or hope to have the molecules that are essential for life as we know it here on Earth, or at least seem to be essential for life, and those are carbon, hydrogen, nitrogen, oxygen, phosphor, and sulfur. And there's a particular molecule that seems essential to life, just so important for life here on Earth, that we should talk about that as well, and that's water. And not just any water, it's water in the liquid state. So what is the sun? The sun is a star. It's a typical star among hundreds of billions of other stars in the Milky Way galaxy. And the Milky Way galaxy is just one of hundreds of billions of other galaxies in the visible universe. Remember, the universe itself might be infinite for all we know, but the visible part at least has about 100 billion galaxies, each containing more than 100 billion, or most of which containing more than 100 billion stars. So we're not short on stars. There are lots and lots of stars. But how long do these stars last? We had to be a little bit more careful about this question. We have to consider the life cycle of stars. Stars don't last forever. So our so let's start with our sun. Our sun, it's been around for 4.5 billion years. And it will persist, we believe, for another at least 5 billion years on what's called the main sequence. So right now it's a star on the main sequence, meaning that it's fusing hydrogen to helium. And during that phase, it's a very slow process. And during that slow process, the star will shine, and its temperature gradually increases with time. So for a star like our sun, there are billions of years on which for which life can form and develop. But what determines the lifespan of a star on the main sequence? Well, it's the initial mass, the mass that star had when it initially formed. We're going to look at that formation process in more detail later in this lecture in a subsequent video. But that initial mass, when the star first formed, is the thing that determines how long that star will last on this main sequence. Counterintuitively, the more mass there is, the shorter the star spends, the shorter time period the star spends on that, the star spends on the main sequence. In fact, the most massive stars end their life quite quickly in a dramatic explosion called a supernova, which will be important later for the discussion later as a parenthetical comment. That process of supernovae is important in generating these heavier elements heavier than iron, but we'll cover that later. So if you're concerned about, a skeptic about the possibility of life forming elsewhere, might suggest that maybe our sun is special in that it's a light star, and other stars are typically much heavier and have a shorter lifespan. That turns out not to be the case. Right? You can ask, so an important question to ask if you're looking for a shelter for life to form elsewhere in the universe, you need to have a significant number of stars for which their initial mass is less than or similar to the solar mass. So are there many of these stars? Well, to get into that, I have to get into a little bit new material, but I'll cover it very briefly. It's something called the initial mass function. And using that, I'll show that, in fact, our sun is a slightly big star. We said it's typical. It's a little bit more massive than the typical star. So what's the initial mass function? The initial mass function, IMF in English, or the acronym for the English term, is a relationship that describes the distribution of masses of stars when they're first formed. Another way of saying it is that the initial mass function provides the relative number of stars as a function of their initial mass, or their starting mass, when they started this life on the main sequence. And remember, they started their life on the main sequence when they first formed and reached 10 to 15 million degrees in their center to bring the protons together, to fuse them and form deuterium, which starts this reaction that allows the fusion to continue on to form helium-4. That's the definition of the main sequence stars. It's fusing hydrogen to helium-4. We looked in some detail at the one possible pathway, the proton-proton chain. So astrophysical observation, so astronomy, supports there being an initial mass function which is universal. It seems to apply almost everywhere in the universe that we've checked, with the possible few minor exceptions. There seems to be a universal initial mass function such that the most probable initial mass of a star is about 1/4 a solar mass. A star with 1/4 the solar mass as its starting mass would have a lifetime on the main sequence of 32 times the lifetime of our sun. So 32 times 10 is 320 billion years. So when I say this is the most probable mass of a star, what I mean is, of course, there's a whole wide range of solar masses, and but if you picked one at random, the most likely initial mass of that star would be approximately 1/4 solar mass. You might get lucky and get a heavier one, or you might get lucky and get by chance you might get a lighter one, but the most likely mass would be 1/4 the solar mass, and a star of that mass would have a lifetime of more than 300 billion years. So our interest in this as coming at this from the point of view of exobiology is that there would appear to be no shortage of stars that are light enough to have a duration on the main sequence, so shining like our sun is now, for time periods of tens of billions of years to hundreds of billions of years.